What if the key to progress was not ancient wisdom, but a new method of thinking? What if centuries of certainty were built on sand, and a bold few set out to rebuild knowledge from the ground up? In the early 17th century, Europe's universities clung to Aristotle and medieval scholasticism, dusty lectures, frivolous disputations, and hair-splitting arguments. Nature's secrets remained hidden behind dogma. Into this stagnant world stepped a visionary, Francis Bacon, who dared to ask if we might start fresh, observing the world directly. Bacon believed that the old approach, debating texts and relying on syllogisms, was leading only to vain notions and blind experiments. He offered something revolutionary, a new instrument of thought that would transform ignorance into power. Welcome to another lecture of the Crash CSS Philosophy series. I am Saima Sadaf, and today we explore an idea that changed how we think about thinking itself, the inductive method. Through the story of Francis Bacon and John Stuart Mill, we'll see how induction, reasoning from particular facts to general truths, became the engine of modern science. Just as Socrates taught us to question proudly held beliefs, Bacon and Mill teach us to question nature with experiments and observations. Their legacy is all around us, in every scientific discovery and every evidence-based argument. Let's dive into how induction rose to prominence and why it matters for CSS aspirants seeking to sharpen their analytical reasoning. The year is 1600. Picture the halls of Cambridge or Oxford. Latin debates echo under vaulted ceilings. Learned men argue over Aristotle's classifications and find theological points. Knowledge means commentary on ancient texts. Truth comes from authority and tradition. Francis Bacon found this state of affairs intolerable. A lawyer, courtier, and polymath, Bacon looked at the intellectual stagnation of his time and saw a tragedy and an opportunity. He lamented that universities had become mired in verbosities and frivolous disputations, chasing trivial questions while practical knowledge languished. The scholastics, in Bacon's eyes, treated learning like an exercise in argument rather than a quest for new truths. He wanted to rescue inquiry from the grips of sterile tradition. Bacon's historical context was crucial. The Renaissance had rediscovered classical wisdom, but now Europe hungered for something more: practical understanding of nature. Explorers were mapping new continents. Galileo was peering through his telescope. Bacon sensed that an age of discovery was dawning. If only thinkers would break free from what he called the idols of inherited dogma. He famously declared that knowledge is power, a motto encapsulating his vision that understanding nature means mastering it. To harness that power, Bacon argued, we must change how we think. It was time to purge old habits of mind and adopt a new method of learning. In this scene, Francis Bacon stands as a herald of modernity, ready to shatter the idols of the mind that kept humanity in darkness. Bacon's critique of the status quo went hand in hand with his alternative vision. He boldly proposed that we set aside blind faith in authority and turn to experience. Instead of starting with grand theories or sacred truths, Bacon said, "Start with doubt. If a man begin with certainties, he shall end in doubts. But if he will be content to begin with doubt, he shall end in certainties," Bacon wrote. This was intellectual heresy to many traditional scholars, but it was the kind of heresy that propels progress. Bacon argued that genuine understanding comes not from assuming we already have the truth, but from patiently investigating reality. In his 1605 work, The Advancement of Learning, he defended the expansion of knowledge and condemned those who mistake the ultimate end of knowledge as mere argument or reverence for the past. For Bacon, the true goal of learning was to improve human life, the relief of man's estate, by uncovering nature's laws. To explain the change he had in mind, Bacon used a vivid metaphor. The scholar, he said, should be like a bee. The old philosophers who spun theories from their own heads were like spiders weaving cobwebs. Those who only collected quotations and observations without reflection were like ants. But the bee gathers nectar from flowers and then transforms it into honey through its own effort. So too should the philosopher gather observations from the world and digest them with rational analysis to produce genuine knowledge. This middle path, combining experience and reason, was, Bacon believed, the true business of philosophy. It was a call to move from armchair speculation and bookish learning to an active investigation of nature. Bacon's new method promised discovery. By observing carefully and thinking clearly, one could derive insights that no ancient authority had ever handed down. In 1620, Francis Bacon published a book with a daring title, Novum Organum, Latin for new organon or new instrument. The title boldly claimed to replace Aristotle's ancient organon, the standard textbook of logic, with a superior tool for acquiring knowledge. At the heart of Novum Organum was Bacon's method of inductive reasoning. Induction means building general principles from particular observations, learning from examples rather than deducing from assumed truths. Bacon insisted this was how we must proceed if we want reliable knowledge of the natural world. He was blunt in his assessment. The old way of reasoning from a few instances or authoritative axioms was childish, too quick to generalize, too prone to error. Old knowledge-building methods were often not based in facts, Bacon observed, criticizing the ill-proven deductions and metaphysical conjecture of the scholastics. Bacon was effectively teaching scientists how to think with evidence, trust no hypothesis until it has been thoroughly tested against reality, and be ready to revise or discard even your favorite theories if the facts contradict them. This inductive discipline was a dramatic shift from the deduction of Aristotle's logic, where one typically started with general premises, often taken on faith or classical authority, and reasoned down to specifics. Bacon turned the process upside down. Start with specifics and carefully work upward. He acknowledged that this approach could be slow and painstaking, by gradual degrees, as he put it, but it would yield knowledge that was solid, useful, and ever-growing. No longer would thinkers simply argue in circles. Armed with induction, they would venture into the unknown and bring back new truths. Little wonder that Bertrand Russell would later hail Bacon as the founder of modern inductive method, a pioneer who helped systematize scientific procedure. Bacon's vision laid the groundwork for the scientific revolution, influencing figures from Isaac Newton to the Royal Society of London, whose founders admired Bacon as an inspiration. Bacon knew that adopting the new method required more than a change in technique. It demanded a change in mindset. Early in Novum Organum, he warned that the human mind is not a clear mirror of nature. It's riddled with distortions and biases. He famously cataloged 4 types of idols of the mind that deceive us if we're not careful. These idols are like false gods that our intellect unwittingly worships, leading us astray. Bacon's 4 idols are: 1. Idols of the tribe, the natural biases of the human race. These arise from our common human nature. We tend to see pattern and order where none exists, or assume our sensations reflect the world as it really is. For example, we might perceive purpose or symmetry in random events. This is a universal human fault. As Bacon put it, the mind hastily and without choice imbibes false assumptions. The idol of the tribe warns us that wishful thinking and hasty generalization are built-in pitfalls of our species. 2. Idols of the cave, the biases of the individual. Each person's mind is like a cave, from Plato's allegory, shaped by personal experiences, education, temperament, and even quirks of personality. One person might favor abstract theories, another loves data. One might be optimistic, another skeptical. These individual caves cause us to see things not as they are, but as colored by our own peculiarities. Bacon urges us to be aware of how our individual cave can distort our reasoning. For instance, a scientist fixated on a pet hypothesis might ignore data that doesn't fit. 3. Idols of the marketplace, the distortions arising from language and social interaction. In the marketplace of ideas, our conversations, the words we read and hear, language can mislead. We often use words without clear definitions, or we assume that if we have a word for something, it must correspond to a real entity. Think of terms like luck or nature. They can be vague or misleading. Bacon warned that arguments can be obscured by the confusion of tongues, as people talk past each other or use emotive language instead of precise terms. Clear observation requires clear language, purged of the idols of the marketplace. 4. Idols of the theater, the grandest illusions, stemming from dogmatic philosophies and theoretical systems. Just as plays in a theater are fictions, Bacon said many intellectual systems are but staged fantasies, worldviews we buy into because of tradition or charisma, not because of truth. Aristotle's cosmic system, Ptolemy's astronomy, the alchemist's theories. In Bacon's view, these were like popular plays, captivating but unproven. He urged thinkers to question these theatrical dogmas and not let any philosophical stage play, whether rooted in Aristotle, Aquinas, or anyone else, hold us back from observing with fresh eyes. Bacon's Idols of the Mind was a prescient catalog of cognitive biases long before psychology would give us those terms. He was teaching us intellectual humility. To do induction well, we must first recognize how our minds deceive themselves. A scientist or analyst must slay these idols, or at least keep them in check, by being aware of prejudice, testing definitions, and doubting grand systems. Only then can we interrogate nature directly without our answers being staged by preconceived ideas. For CSS aspirants, Bacon's lesson is clear. Beware of biases and ideological preconceptions. Whether analyzing a social issue or a case study, remember that our minds can be idol factories. We must continuously check our biases at the door of inquiry, just as Bacon advised. Having cleared the ground of false idols, Bacon set forth a concrete approach to investigation. His method was empirical and iterative, resembling what we now call the scientific method. In Novum Organum, Bacon described how a researcher should systematically search for causes. He even outlined something akin to experimental tables. For any phenomenon under study, list all the cases where the phenomenon occurs, and all the cases where it does not occur, and even cases where it occurs in varying degrees. By comparing these lists, one can isolate the factor that consistently appears when the phenomenon appears and is absent when the phenomenon is absent. In other words, Bacon advocated the germ of what would later be called the method of agreement and difference. If one factor is the only difference between a successful battle and a failed battle, then perhaps that factor is the cause of success. Through such logical comparison, the investigator homes in on likely causes. Bacon illustrated this with examples and called the preliminary conclusion a first vintage, an initial hypothesis about the cause. Importantly, this first induction was not the final word, but a starting point to be scrutinized and tested against further evidence. In this way, knowledge moved forward in stages, each hypothesis refined or refuted by new observations. Bacon's process might sound familiar because it prefigures the procedures of modern science. We observe, hypothesize, test, and refine, exactly the spirit Bacon championed. He believed true knowledge grows cumulatively. Researchers could slowly but accurately build an essential base of knowledge from the ground up by repeating this cycle. Under Bacon's influence, science became a collective enterprise of fact-gathering and inductive reasoning. This approach was soon put into practice. Physicians like Thomas Brown in the 17th century used Baconian empiricism in debunking common myths. Institutions like the Royal Society adopted Bacon's creed of nullius in verba, insisting that claims be demonstrated, not just argued. The impact was enormous. By insisting that theories be grounded in observable facts, Bacon helped humanity escape what he called common induction, the lazy generalization from too few examples. Instead, he gave us a disciplined way to interrogate nature. Even with its slow, step-by-step rigor, Bacon's inductive method carried an optimistic promise. Many small empirical certainties could eventually lead to great general truths. He likened the project to building a pyramid, broad at the base with observations and narrowing toward a point of general principles, a point that might even reach toward laws ordained by the Creator. For us today, and especially for aspiring civil servants, Bacon's methodical approach is a reminder that sound conclusions, whether in science or policy, require patience, data, and an open yet critical mind. Grand theories and sweeping reforms must rise from verified facts, not the other way around. This is induction in practice, climbing the ladder of evidence one step at a time until doubt gives way to well-earned certainty. Now, we fast forward 2 centuries to the 19th century. The scientific revolution sparked by Bacon and others had transformed the world. By the 1800s, experiments and induction were widely accepted as the way to knowledge. But how exactly does one make a strong inductive argument? Enter John Stuart Mill, born in 1806, one of Victorian Britain's greatest minds. Mill is often remembered for his works on liberty and utilitarian ethics, but he was also deeply concerned with logic and scientific reasoning. In 1843, he published a thick volume entitled A System of Logic, Ratiocinatively and Inductive. In this work, Mill took Bacon's vision of inductive science and sharpened it into a set of clear rules. The Baconian method, Mill felt, needed to be elaborated and clarified so that scientists could have a reliable toolkit. Mill was, in a sense, Bacon's intellectual descendant, carrying the inductive banner forward into an age of railways, telegraphs, and industrial research. Mill had been educated rigorously from childhood by his father, James Mill, and he grew up steeped in the empiricist philosophy of Locke and Hume. David Hume, in the 18th century, had famously raised the problem of induction, questioning how we can logically justify generalizing from past experience. John Stuart Mill was well aware of Hume's challenge, but he was a practical philosopher. Rather than despair at induction's philosophical puzzle, he aimed to make induction as robust as possible. Mill's approach was to analyze how we can systematically infer causal relationships from observed data. He observed that scientific discoveries often come from noticing patterns. When certain conditions are present, a phenomenon occurs. When they're absent, it doesn't. Varying one thing changes another, and so on. Mill believed if we articulate these patterns as formal methods, we can guide the process of inductive inquiry and minimize error. In doing so, Mill codified induction in a more analytical way than Bacon, reflecting the more advanced state of science in his time. Importantly, Mill did not see himself as overturning Bacon, but as building on Bacon's foundation. He admired how Bacon had advocated thorough experimentation and rejection of superstition. What Mill provided was a more detailed logic of induction, a way to tell when a collection of facts actually justifies a general conclusion. If Bacon was the architect of the house of induction, Mill was drafting its instruction manual. As one historian put it, Mill's 1843 system of logic shed further light on issues of causation and distilled inductive reasoning into concrete principles. This effort reflects a broader trend of the 19th century, the desire to systematize knowledge. Just as chemists were writing the periodic table and biologists were classifying species, Mill wanted to classify the forms of inductive inference that lead to valid conclusions. The result was a famous list of 5 methods, to which we turn next. John Stuart Mill's enduring contribution to logic is encapsulated in what we now call Mill's methods, 5 techniques for inductive reasoning. These methods are essentially guidelines to establish cause and effect from observational evidence. Mill presented them in A System of Logic, and they have been taught in logic and science classes ever since. Let's briefly walk through each of Mill's 5 methods, as they provide a neat summary of how to think inductively. Method of agreement. If multiple instances of an event or phenomenon share only one common factor, then that factor is likely the cause of the event. Mill put it formally: if 2 or more instances of the phenomenon under investigation have only one circumstance in common, the circumstance in which alone all the instances agree is the cause of the phenomenon. For example, if several people at a dinner get food poisoning and the only dish they all ate was the salad ingredients are the prime suspect cause. The strength of this method is in highlighting a common thread across occurrences of some effect. Method of difference. If an instance in which a phenomenon occurs and an instance in which it does not occur are exactly similar in all circumstances except one, then that one differing circumstance is likely the cause. In plainer terms, compare a case where the effect happens to a case where it doesn't, and if everything is the same except one factor, then that factor probably makes the difference. For example, 2 patients have identical symptoms, except one took a certain drug and got better, the other did not take it and remained ill. By the method of difference, the drug's presence or absence is the key causal factor. This method is essentially the logic behind controlled experiments and A/B testing. Hold everything constant, change one thing, and see if the effect appears or disappears. Joint method of agreement and difference. This method simply combines the first 2 for greater rigor. It says that the likely cause is the one identified by agreement across occurrences and confirmed by difference in non-occurrences. In practice, this means you find the common factor in all cases where the effect happens, and also show that when that factor is absent, the effect doesn't happen. The joint method strengthens our confidence in a causal inference by approaching it from both angles. Method of residues. Subtract from a complex phenomenon the parts that are already explained by known causes. Whatever remains of the phenomenon should be attributed to the remaining possible factors. Mill suggested that after accounting for known causes in a situation, any residual effect must have whatever factors are left as its cause. For instance, suppose you know chemical reactants A and B produce outcomes X and Y respectively in a reaction, but you observe an additional outcome Z. By the method of residues, Z must be due to some other element or condition C not yet accounted for. Scientists often use this logic when they say, "We've explained part of the effect. Now what's left unexplained indicates a new factor." This method led to many discoveries, e.g., the planet Neptune was hypothesized as the residue cause of anomalies in Uranus's orbit after accounting for known planetary influences. Method of concomitant variations. If changes in one factor correspond consistently with changes in another factor, then the two are likely causally related. This addresses scenarios where we can't isolate a single factor completely, but we can observe degrees of correlation. For example, if increasing the dosage of a drug consistently yields a stronger response in a patient, and lowering the dosage yields a weaker response, then by concomitant variation, the drug is likely influencing the response. Mill's insight here is that correlation can imply causation when everything else is accounted for, especially if we see a graded effect. This method is used widely in social and natural sciences. Whenever researchers say, "the more X, the more Y," they are invoking concomitant variation as evidence of causal connection. Bacon and Mill, separated by over 200 years, together laid the foundations for modern scientific and analytical thinking. The inductive method championed by these 2 thinkers became the cornerstone of the scientific revolution and the Enlightenment. Bacon's influence is evident in the way science evolved after the 17th century. Experimenters in the Royal Society explicitly cited Bacon as an inspiration, embracing his call to focus on facts and practical discovery. Sir Isaac Newton famously said, hypotheses non fingo, reflecting a Baconian ethos of letting the data speak before any speculation. In the 19th century, Charles Darwin would echo Bacon's approach, writing, I worked on true Baconian principles and without any presupposed theory collected facts on a large scale. This patient accumulation of facts before theory allowed Darwin to induce the theory of evolution from observations around the world. Such is Bacon's legacy, the belief that through methodical observation and induction, even profound truths can be uncovered without presuming them in advance. John Stuart Mill's legacy is seen in how we conduct investigations and handle evidence. His focus on identifying causes through systematic comparison pervades scientific methodology, statistics, and even investigative journalism. Whenever researchers design a controlled experiment, they are using the method of difference, keeping all factors the same except one to test its effect. Whenever epidemiologists seek a common exposure among outbreak victims, they are applying the method of agreement. When policy analysts examine correlations and control for other variables, they invoke concomitant variation and residues. In short, Mill's logical rigor in induction helps us not jump to conclusions from coincidences. It pushes us to verify causal links. Moreover, Mill's work influenced the philosophy of science in the 20th century. Thinkers like Karl Popper built on Mill's ideas, albeit critically. Popper argued that science advances through bold conjectures and rigorous attempts to refute them, which is a twist on induction. Yet even Popper's falsification relies on the idea that evidence can and must test our ideas, a very Bacon and Mill principle. Of course, induction has its philosophical challenges. David Hume alerted us that no matter how many white swans we see, logic cannot guarantee that the next swan won't be black. Bertrand Russell illustrated Hume's point with a darkly humorous example of a chicken that inductively concludes from daily experience that the farmer always comes to feed it, until one day the farmer comes to wring its neck. This problem of induction reminds us that inductive reasoning yields probability, not certainty. However, as Russell and others recognized, without induction, we'd be paralyzed. We rely on it for virtually all empirical knowledge. The success of science and the technologies it spawns is a practical vindication of induction. We have antibiotics, electricity, space travel, none of which would exist if we hadn't assumed that patterns observed so far will likely hold in the future. Induction may be philosophically less than certain, but it is pragmatically indispensable. Thank you for watching and being part of this journey into powerful ideas that shape the way we think. If you found this lecture helpful, don't forget to like, subscribe, and press the bell icon for more. See you in the next video, where we continue exploring ideas that sharpen your thinking.